Hello and welcome. I'm Karen McFarland, the punk rock professor, here to bring you clear and concise tools to help you crush chemistry old school style. We're going to be talking about weak acids today, and then we're going to head into another video into buffers. But we need the starting point of talking about weak acids because buffers consist of weak acids and their conjugate bases. But let's head in and talk about weak acids to start. Okay, so our example weak acid that we're going to be talking about is acetic acid. Very common acid. It is the component of vinegar, and it works very well as a good example since it's in everyday life. So the formula of acetic acid. It's not the simplest one, but it is so common. Let's take a look at it. This is what we call an organic acid, and here is its formula. Okay, so here's our acetic acid, and because we're going to be looking at everything in aqueous solution, we want to make sure we include that phase there. Okay, so when we dissolve acetic acid into water, it can then react with the water, so to speak. And so we're going to write out first showing acetic acid reacting with a water molecule and what our products are. And then we're going to look at kind of a shortcut and how we can write that same equilibrium. Okay, so when we first write this out, here's our acetic acid. And I am going to now write out our equilibrium that we're interested in with acetic acid in water. Okay, so we've got our acetic acid, and this is a weak acid. And so that means that it's not going to behave quite like strong acids do. When it is put into water, so here's our aqueous phase, and here's our water, and that's just liquid phase. We're looking all at this at 25 degrees Celsius. And we've got an acid-base reaction happening here. And very specifically, it's a Bronsted-Lowry type acid-base reaction, which means a hydrogen ion transfer. So the hydrogen ion transfer is going to be starting at the acid and going to the base. And in this case, our water molecule is acting as the base. It will be accepting that hydrogen ion. All right, so we've got an equilibrium going on here then. And this acting as the acid and giving up that hydrogen ion to the water molecule, our products are then, this is what we call the conjugate base of acetic acid. It has lost that hydrogen ion, H+, and so this acetate ion that is left has a negative charge there. So still an aqueous solution. And then our water molecule has taken on that hydrogen ion, that H+, and so that is now the hydronium ion that is in solution. Okay, as a side note, we can also note that we have charge balance in this reaction. We should always have charge balance in any of our chemical reactions where it is neutral over here, neutral, neutral, and here's a minus and a plus, also neutral on this side. Okay. So this is looking good, but I wanted to point out that there is a shortcut that I mentioned earlier, and that is that we can ignore the water molecule. It is there, but it allows us to simplify some of the equations we write out, and it's also really conventional to do this. So it is common that we see hydronium ions, but here's another way to write out this equilibrium. And that is that we show the acetic acid. Essentially, the way we're depicting this is it is just breaking apart into acetate and H+. Okay, so the H2O is here as a reactant. The H2O has gained an H+ over here to make the hydronium ion, but it turns out just showing H+, it really does work. So I'm going to be using this convention from now on, but Don't be alarmed if you ever do see H3O plus in place of H plus in any kind of calculations in other places. Okay, so this is where we're at. We are acknowledging that we've got this equilibrium going on. And then the next thing we want to talk about is the fact that acetic acid is a weak acid. And what does that mean? All right, so a weak acid mostly stays together. Okay, so this is considered a weak acid. Thank goodness, it allows us to actually consume vinegar, right? So a weak acid mostly stays together as a molecule. So this mostly exists in this molecular form over here. All right, meaning that it is mostly not breaking apart and giving us a lot of hydrogen ions. That again, if we were to spill a strong acid on us, we would want to wash our hands right away. If we get vinegar on us, we might wash our hands, but it's more because we don't want the stinky vinegar smell or whatever. It's not going to hurt us immediately if we don't wash our hands. So that means that the acetic acid is mostly staying together as a molecule, but it does break apart a little bit. Okay. And when we say a little bit, that means that depending on the weak acid, we don't know. All different weak acids behave differently. And so it's not like I can say all weak acids are going to break apart to this extent, 5% or 10% or 3%. No, they're all going to break apart to different degrees. And so we need to have extra information about each weak acid to be able to assess how much is it breaking apart, and then what kind of questions can I ask and answer that are related to that. Okay, so we do have some, okay, so we have a few do break apart and give these ions. All right, so as we know with vinegar, we do get a few of these hydrogen ions that give us that sour taste that acids do. Okay, so let's delve in and get a little bit more quantitative and figure out how do we know to what extent acetic acid breaks apart. All right, and to do that, we need a bit of information that needs to be given to us. We need to go look it up on a table, or if we're taking an exam, we need to be given the information that is going to tell us to what extent our acetic acid breaks apart. Okay, and that information is given to us in the form of an equilibrium constant. Okay, so generally speaking, equilibrium constants, they are a ratio of products over reactants. Okay, that's really generally speaking. It's tied in with the stoichiometry, but we're looking at essentially a ratio, products over reactants. And so with acid ionization constants, that is essentially the equilibrium constant for acids breaking apart, ionizing. We actually get a special value, or I guess a special designation. They're called Ka values, but it is an equilibrium constant. Okay, so instead of writing KEQ, a generic equilibrium constant, if we're talking about a weak acid, we're going to put a little A there for acid. And in the case of acetic acid, our products were, if you recall, the acetate ion and the hydrogen ion. Our reactant was the acetic acid molecule. Okay, and right here is a great example of one of the reasons why it does work to ignore the water, because water is a pure liquid. It's not going to appear in the equilibrium constant expression anyway. So this is going to work great regardless of whether you have H plus there or H3O plus. Okay, so here's our equilibrium constant expression, but this has a value. And as I said, you can look it up on a table, and specifically for acetic acid, its value is 1.8 times 10 to the minus fifth. So one thing we can look at is to just consider, what does this value mean? What information can we get from this just qualitatively? What can we say about acetic acid? And one thing we can say is this is a pretty small number, relatively speaking, and it is less than 1. Okay, so a small number, less than 1, is telling us we have more reactants, the acetic acid, than we have products, or ions. There is some good information telling us, yes, indeed, that acetic acid molecule is staying together for the most part. We're only getting a few of those ions breaking apart. Okay, what else can we do with this? Well, we could find out exactly what the pH would be expected to be for a solution of acetic acid. So let's see how we can do that kind of calculation. Let's first ask a question, a specific question, okay? So imagine we've got a solution of acetic acid that has a known concentration. Okay, so let's say we have a known concentration of acetic acid, and it is 0.6 molar. Okay, we could ask the question, what's the pH of this solution? Let's figure that out. Okay, what is the pH? And we need to know what the equation is for pH, don't we? Okay, so pH can be calculated by the minus base 10 log of the hydrogen ion concentration. All right, so if we want to know the pH, that means we need to figure out what the hydrogen ion concentration is for this solution that we're talking about, this acetic acid solution that's 0.6 molar. So let's see if we have enough information to figure this out. We have an equilibrium constant expression. We know the value of the equilibrium constant. And what else do we know? Let's see. We've got acetic acid concentration that we need to know, and lo and behold, that has been told to us. Yay. Okay, we know the Ka value, that's great. Here's what we're trying to find, H+. Okay, what about acetate? All right, do we know the concentration of acetate? So this is where we acknowledge all we have in solution is this acetic acid, and there is a 1-to-1 stoichiometry. When that acetic acid molecule broke apart, it gave us, for every one of those acetic acid molecules, it gave us 1 acetate ion and 1 H+ ion. So we have a 1-to-1-to-1 stoichiometric ratio. And so that means that the concentration of these two ions is equal. Okay, that's going to be really helpful for us. So why don't we figure out, all right, what is it we're trying to find? We're trying to figure out what hydrogen ion concentration is. Let's do one of those things we do in algebra sometimes. Let X equal hydrogen ion concentration. And we just acknowledged from stoichiometry that this is equal to the acetate ion concentration. Okay, so since these are equal, we're just calling it X because X is easier to write as we do our calculations. That's really the only reason. All right, so that means that we have X times X in this equation. So we're going to rewrite this Ka expression down here now that we've set X equal to H+ and acetate. So we now have X times X times X, that's X squared. We know that this is 0.60 molar. And notice I'm not putting in units there. I'm going to talk about that in a second. And we know that this is equal to 1.8 times 10 to the minus 5th. Okay, few things to talk about. One is, some of you might have been going, wait a minute. If we have this acetic acid that's breaking apart and forming these ions that we're calling X, doesn't that mean we've lost a little bit of that acetic acid? And shouldn't it be a little bit less than 0.60? And I would say you are very clever, okay? But I'm also going to say you're clever, and guess what? We get to take a little sneaky approximation, because these are weak acids. They're not breaking apart very much. And so we get to make an assumption that the amount it breaks apart is so small compared to the concentration that we're dealing with. Okay. Disclaimer, that's not always going to be the case. That is something you can check for. But when you're taking general chemistry and you're first learning about weak acids, we're going to be able to make this assumption. Okay, so we can move into where that's not going to be the case, but that is where it gets more complicated. We're starting the fundamentals here. Okay, so yay, we get to make an approximation. And so, therefore, this is 0.60 molar. Okay, then you say, where'd the molar go? Where'd the units go? Okay, so 4 reasons. Once again, if you get into maybe sophomore, junior, senior level physical chemistry course, you can learn exactly why our equilibrium constants do not have units. And so because in the end, this value doesn't have units, I just start dropping them at this point. Okay. They're not here because they end up canceling out for various reasons that have to do with something called activity. We don't have to worry about that. Excellent. Okay. So what we do have, though, is we have a nice equation here that looks really solvable at this point. I'm pretty excited. So what I'm going to do is multiply both sides by 0.6, okay? And then that allows us to, I want to keep that squared. Multiply both sides by 0.6. I'm hoping I did this calculation over here handy. And then once we get this squared value, we'll then take the square root of both sides, and that gives us our final value of X, which we defined as the hydrogen ion concentration. Okay, and that is 3.3 times 10 to the minus 3 molar. 3.3 times 10 to the minus 3 molar. And here you might be saying, wait, now you just invoked the units out of nowhere? Yes, I did. And part of this is that we know that X equals something that is a concentration that we're talking about. And yes, you can invoke those concentration units of molarity here. Okay, you are allowed to do that, I swear. Okay, excellent. So we now have our concentration of hydrogen ions in a 0.6 molar concentration solution of acetic acid. Whew, I think we're ready to calculate the pH, right? Okay, our pH is minus log of H plus. So let's make some room here. I think we've done all this. That's great. So I'm going to erase this so that we can front and center calculate the pH of this solution. pH equals minus log of H plus. Okay, so in this case, that means it's minus log of 3.3 times 10 to the minus 3. Oh, here we get to play with units again. Logs really mess with units, okay? But in any case, we are taking the base 10 log of this value, and then we are taking the negative of that value that we get, all right? And our result is 2.48. All right, so here's our pH, our final pH of the solution, 2.48. Let's think about this. pH scale goes from about 0 to 14. And we see that this acetic acid is falling below 7. 7 is neutral, and it is down there. That is in the acidic region. That is what we would expect. That's something we always want to do. Whenever we get a final result, take a look at it. Does this make sense? And yes, it does. We're looking at an acid, and it is down there in the acidic region of the pH scale. Okay, so in another video, we're going to take this same acetic acid solution. We're going to create a buffer out of it. So watch for that one. But it is time for the bonus track. Yes. Okay. So I am wearing a t-shirt of a fabulous band from Salem, Oregon. You're lucky if you catch them because they don't play very often. They are called Monoplane. Okay. Can you see my old t-shirt? I hope so. Okay. They're so much fun. They're all magnificent people and musicians. And like I said, it's a rare gem of a find if you can either see them play live or catch any of their music. And the bonus track I'm going to give you is their song Cherry House. That song was named after a place called Cherry House that recorded, is a recording studio, and a lot of bands recorded there. One of my bands recorded there once. It is no longer a recording studio, sadly enough, but that song lives on and you should check it out. So thank you so much. If this helped you at all, like and subscribe. It helps me make more videos. I love doing it. Thank you for being here with me, and I will catch you next time.